My name is Loren Stewart with Exida. Quickly, just a little thing, if you have any questions, go ahead and type them into the panel on the right-hand side. I will try and check it periodically throughout the webinar, but sometimes I'm not the best at that. So at the end, I will definitely make time for any questions that you may have. So if you have anything, go ahead and write it in the box. If I remember to check throughout, I will. If I don't, we will go back throughout the slides and we'll definitely check all questions. We can even go back if you have a question on a particular slide. Today, we will be talking about mechanical failure rates, explaining the differences. A little bit about myself. My name is Loren Stewart. I graduated from Virginia Tech with a BS in me. I started manufacturing or in the manufacturing and custom design area of engineering, and I currently work for Exida supporting their mechanical customers. I work on safety certification and assessing safety products along with researching stiction and failure rates and the 2H initiative. A little bit about Exida. We have three major categories. The base of our specialties is our knowledge base. We have our training, our tools, our experts, our library. We also have our life cycle services. And at the very top, we have our assessment and certification services. Exida is located all around the world. We have a new regional office in the Middle East. We're really excited about that just opening. And so as you can see, no matter where you are or where your customers are, we have an Exida location close by that can help you out. We have four main industry focuses here at Exida. We have our OEM, our system design, our end user, and our engineering contracting. No matter where you fall into the four sections in the industry focus, we have books, we have tools, we have certification, we have services, and our professional development. So no matter where you are in which part of the industry, we can have different specialties to help you. And this is showing our main products and our service categories. So we have our consulting, which would be the IEC 61511, 62061, and ISO 26262, and alarm management and control system security. We also have our engineering tools, our Excellentia, which I'm sure a lot of you have heard of, which involves our FACS, our SIL selection, our LOPA-X, our SRS, and our SIL verification tools. We have our safety case tool, our FMEDA, our SIL alarm, SIL stat, and CyberFAX tools. We also have product certification, and that goes along with functional safety IEC 61508, control system cybersecurity, and network robustness. We have training on process safety, control system security, security development, alarm management. We can come to you, you can come to us, so it doesn't matter how you would like to be trained. We can teach you anything dealing with functional safety. Also, we have our reference materials. We have our databases, our tutorials, our reference books and market studies and textbooks. And finally, our professional certification. We have our CFSE and P, and that would be our Certified Functional Safety Expert and Professional. And we have subspecialties in automotive, hardware, machinery, process, software, and newly we have our CACE and CACS programs, which are Certified Automation Cybersecurity Expert and Specialist. And a little bit about our reference material. We get really excited to let everybody know that we've authored the most industry references for automation safety and reliability. And we have a new, we're just taking pre-sale inquiries right now. We have a new industry data handbook on equipment failure data. This is the 4th volume. So like I said, we're just taking pre-sale right now. We're really excited. We've put a lot of time and effort on the 4th volume of the SCRH. So why you're here today, I'm assuming, not to necessarily hear all about exida, but to talk about the webinar. What we're going to discuss today are the distinction between failure rate prediction and failure rate estimation methods, details about the procedures used to obtain generic failure rates for certain mechanical equipment using FMEDA predictions and ARITA estimations, along with other methods used in industry today, specific equipment failure rates compared, and when differences in the results exist between the 2 or more methods, we're going to talk about some plausible explanations for the differences. We're also going to speak of equipment examples, including representative of topside equipment items and subsea equipment items. Relative merits for each method are discussed along with comparisons to industry database and field studies. And finally, we're going to talk about what is a realistic failure rate for mechanical devices, and what do you do if you find yourself looking at unrealistic numbers? Because that can happen and might happen to you, so you want to be prepared if it does. I like to start off with this webinar talking about what is functional safety and what does IEC define functional safety as. So IEC 61508 says the functional safety goal is the automatic safety function will perform the intended function correctly, or the system will fail in a predictable or a safe manner. So that's what we're talking about when we speak of functional safety, that it either automatically performs the intended function correctly, or it's going to fail in a safe or predictive manner. So we're going to start by looking at the detailed safety life cycle. And we're zooming in on the middle of the safety life cycle here. As you can see, it starts on this slide at step 8, which obviously isn't the case, but we wanted to zoom in because it's very large and take a look at step 11. And that is the SIF conceptual design, reliability, and safety calculations. So this is a major portion of what you're going to do to determine what sill level you might need and what risk reduction you need to have receive a certain sill level. And looking at what we circled in red, as you can see, what you need for the safety calculations are manufacturer safety manual and failure rate database. So you're going to make sure you need realistic failure data for mechanical components in this stage, because if you are using unrealistic numbers, you can use unrealistic numbers for safety calculations, and your calculations are going to be wildly optimistic possibly. At that point, you're going to produce risk reduction factors and sill level that you think you might achieve that you might not have. So that is why we are taking a close look at realistic failure data and why it is so important. What we hear is some people say that there's no such thing as realistic failure data, but many others are very confident in failure data. So where does failure data come from, and how do different methods compare? There are 2 fundamental techniques for getting failure data. Your first technique is failure rate estimation techniques. And this is estimating failure rates based on failure data. You also have failure rate prediction techniques based on test results or design strength analysis. We're going to look at different ways to be able to get failure rates for each of the estimation and the prediction. We're first going to look further into the estimation. So failure rate estimation techniques is estimating the lambda or the failure rate based on failure data. And there's 3 methods in use. You can look at manufacturer field return data studies, at industry databases, and end user failure data studies. Of course, there's going to be positives and minuses for each case and examples for each case. So we're going to look at each one of these a little closer. So first is the manufacturer field return study. So the positive is this is real data, and real data is an amazing thing to have. You're not necessarily estimating, you're not guessing, but you're actually having real data come in. The negatives are that the calculation methods vary widely. You cannot know what percent of actual failures are returned. If you have a very, or not necessarily very, but if you have an inexpensive item compared to the entire system, you might only get 50%, if even that, returned to you. It might be cheaper for your customers to necessarily throw it away and order a new one instead of going through the whole RMA process. So you might not even know that you are receiving some failures. Another negative for this type of field data collection is there's different definitions of what a failure is. So many manufacturers classify return items as a failure only if manufacturing defect is found. So there are many items returned marked no problem found or systematic failure. And then they do not count as a failure in the manufacturer field return studies. Calculations are sometimes done when operational hours are estimated based on shipping records, and it is assumed that all failures are returned. Both of those, the hours based on shipping records, there's no time lapse or shelf life. That's optimistic, and also assuming all failures are returned is optimistic. Adding those together, that can be very dangerously optimistic. However, the data can be extremely valuable to identify root causes and to compare to establish lower bounds on failure rates. So although it might not be the best way to say it's your only way of getting failure rates, it's definitely very valuable to have that lower bound. The next method is the industry database. And once again, the huge positive, this is real data. There's the major problem with this is there's not a lot of data available. There's different definitions of failures. Once again, one company might say this is a failure while the other company might say it's not. Also, it's hard to not just throw all of the merging technologies into one category when you have different applications and different technologies. So many industry databases merge all technologies together, which is totally understandable given the data that they receive. And then there's a lack of a fault isolation, once again. One of the most respected industry databases is FMEDA, and they are operated by DNV in Norway, and the data analysis is by Sintef in Norway. FMEDA provides very useful data on process equipment, and it's kept up to date with the latest public release in 2015. We were very excited. The new FMEDA book just came out. We received ours a couple months ago, and we could not wait to get it. This is to take a quick look inside the FMEDA book. It provides a total failure rate based on a given population and recorded operating hours. So for this example, for a pressure transmitter, there's 32 units in the population and 1.12 unit operating hours. And it states a total mean failure rate for an operation time as 420 fits. And finally, we're going to look at end-user field failure studies. Field failure studies with sufficient information represent a rich opportunity to obtain failure rate and failure mode information about a product in a specific application. Once again, the major positive is it's real data. A negative is that variations of the amount of data collected are huge. Once again, there's different definitions of the word failure and what each company considers a failure. They categorize and merge technologies that might not all be the same or appropriate for appropriately put in the same category, and the lack of fault isolation. So after performing dozens of studies, exida recognized that data collection process varies by almost an order of magnitude or sometimes even more. You have to look at when a failure report was written, what is the definition of a failure, are the as-found conditions recorded during a proof test, what are operating conditions. There's a lot of information that can vary. One of the main things that can vary, once we said, is the definition of failures. And this comes into play as what a random and what a systematic failure is. According to IEC 61508, random failures are failures occurring at a random time which result from one or more degraded mechanisms. A systematic failure is a failure related in a deterministic way to a certain cause, which can only be eliminated by the modification of the design or the manufacturing process, operational procedures, documentation, or other relevant factors. So as you can see, there's kind of a gray area. The definitions seem to qualify it and seem to be able to let you understand that there's a difference, but as you can assume, there's a lot of examples where it can kind of fall in between. So there's not necessarily a consistent interpretation. As an example of this, exida sent out a survey to a bunch of people on our mailing list and gave them examples on a specific example and asked if it was a random, systematic, or end-of-life failure. Here's one of the examples we sent out. It talked about a failure occurred when a de-energized to trip remote actuator valve snapped closed and shut down the process during normal operation. The failure was traced to the PLC logic solver rated to 50 degrees C. When an output module failed de-energized. A component in the output module, a transistor, had failed such that it could no longer conduct current. The ambient temperature was quite hot that day at 55 degrees C. An X-ray of the transistor showed a burned out bond wire, likely due to an electrical overstress. Now, as you can see, 4% thought this was an end of life. Almost 40% said systematic failure, and more than 50%, 57%, said random. As you can see, there's not much agreeing. a lot of people say, oh, it could be a random failure, it could be a systematic failure. The next answer, or the next question was, a maintenance technician routinely checks and adjusts the trip points on a generator activation relay. The procedures for checking and adjusting the relay were correct. Although a rare event, occasionally a mistake is made with the adjustment. In one case, the trip point was set too low, and the power generator did not start as needed, and a power system failed. As you can see, once again, we have 57%, but this time it's for systematic, and 43% for failure. No one thought this was an end-of-life failure. So it's not quite, but almost 50-50%. So some companies, almost 50% of companies would say that, oh, this was a random failure. This counts as a failure in our reports. But 57% of companies would say, oh, this was a systematic failure. This should not count against us as a failure, and they would not count this as a failure. So as you can see, it varies. The definition of failure, even though it's a gray area, can vary from company to company and can very much impact failure rates if they were just using field failure data to determine the failure rate. Next, we're going to take a look at the predictive method of getting failure rate. So failure rate prediction techniques are predicting the lambda based on test results or design strength analysis. The B10, there are two methods. The B10 data, which is based on cycle testing for mechanical, electromechanical products, and it assumes application has constant dynamic operation, and an FMEDA, which is a predictive technique developed by engineers here at Exida and uses component database that accounts for design strengths versus a predefined environment. We're first going to look at the B10 or the cycle test failure data. So the B10 method uses cycle testing data. The cycle testing is done on a set of products. It has to be greater than 20 to count for a B10 failure, and they must be cycled until 10% of the units under the test fail. The number of cycles until failure is called the B10 point. 10%, 10, you know. The B10 number of cycles is converted to a time period by knowing the number of cycles per hour in any particular application. And a failure rate is calculated by dividing 10% of the failure count by the time period. The dangerous failure rate is assumed to be 50% of the total, and the safe failure rate is assumed to be 50%. And furthermore, it assumes that no other failure modes exist. So the B10 method assumes that there's a constant failure rate during useful life, and during the useful life is due entirely to premature wear out, and all other failure modes are insignificant. But research shows other failure modes become significant when these products do not move frequently, and failure modes become significant if a product is static or motionless for even just 100 hours. So we're going to take a look at the B10 failure data and how it applies to solenoids, actuators, valves, everything like that. So when O-rings and other seals are part of a product, many failure modes become significant when the product remains static for a week or more. These include stiction, cold welding, corrosion, binding, everything like that. Most of these failures are dangerous. Therefore, the B10 data point is not applicable to most applications, including the process industry applications or any safety or functional safety or safety system related product. So the next predictive method technique is an FMEDA, or Failure Modes, Effects, and Diagnostic Analysis. So FMEDA is a predictive failure rate method developed by engineers here at exida. It performs a study of each component and how the component failure rates will affect the device. It will estimate or test how well automatic diagnostics and proof tests will detect the component failure. Component failure rates are a function of the operating environment. Therefore, a FMEDA analysis is done for a defined one or more defined environments. And as you can see, this chart is the exida environmental criteria broken out into 6 profiles. As you can see, you have the cabinet mounted or climate control, general field mounted with self-heating, subsea, offshore, and process wetted. When we do a FMEDA here, we will pick one or more than one of these profiles and do a complete analysis per component for each profile picked. So the FMEDA is done for each defined environment that the device can withstand. So using a component database, failure rates and failure modes for a product can be determined. Useful life can be predicted, and proof test coverage can be predicted. So from the component database, where you have your failure mode and distributions and each component failure rate, you calculate the FMEDA, which in return can find the product failure rate, the product failure mode, and the diagnostic coverage. So I wanted to give you a kind of close-up look at a FMEDA result and what it looks like when a FMEDA is actually done. So a FMEDA analysis shows differences in design, applications, and operating conditions. So this is an example for a double port guided valve. At the top charts are all in clean service, and the bottom charts are all in what is considered severe service. So you have failure categories. It's broken down into fail safe, fail, dangerous, undetected, and no effect failures. And you also have your close on trip, full stroke, and tight shutoff, and open on trip. And for each one of these categories, you have a failure rate. The accuracy of a FMEDA depends on the accuracy of the component database. The component database must include failure rates and failure mode distribution for each component as a function of one or more operating profiles. The useful life of each component must also be listed as a function of each operating profile. As I like to say, garbage in, garbage out. If the FMEDA or the component database is not well calibrated, the numbers you will get from your FMEDA will be worthless. So you want to make sure that the component database has been calibrated and makes sense. So when you do make your FMEDA, it is an accurate number. So here at exida, we have our database is based on calibrated by field failure data. We have collected over 200 billion unit operating hours of field failure data from the process industry. As you can see, it's just a huge circle. You have your field failure data, which calibrates the public component failure database, which are used in FMEDAs. FMEDA analysis results in safe detected and dangerous, or safe failure rates and dangerous failure rates and the useful life. You take these and compare it to product level failure rates and mode. And you use the field failure data to also compare product level failure rates in failure mode. And it just keeps on going in large circles. The more information we have, we calibrate, and we keep going around and around. This 200 billion hours of field failure data include all three sources of the estimated failure rate data: the manufacturer field return studies, the industry database, and end user field failure data studies. So we make sure to cover all three of the estimation techniques in our database. So I'm assuming this is the large portion of why everybody is here. How does this method of failure rate compare? We start with looking at some pressure transmitters. So we take a look at the ARETA page, and this was the example we looked at earlier. There are 32 pressure transmitters in the ARETA book for with a mean failure rate of 420 fits. And as you can see, there are 35 FMEDAs that we have done on pressure transmitters, and we've compared, those are the blue diamonds all around. And as you can see, we have our exida FMEDA average, we have the ARETA field data mean, and the Dow field data study. And as you can see, overall, there are some FMEDAs that are on the high end and FMEDAs on the low end, and that would represent a more complex design and a more simplistic design. But all three averages or means compared pretty well. The exida FMEDA average is a little somewhat pessimistic, or a slightly higher failure rate, which is what you would want out of a predictive analysis. You wouldn't want your predicted failure rate to come under what your failure rate actually is. Next, we're going to look at a solenoid control valve. In the ARETA book, we have a solenoid population of 4,718 units for 18.2 billion operating hours, and a mean failure rate of 760 fits. And as you can see, the solenoid control valve data, there's two different types of exida solenoids. We have the spool solenoid, which are the higher three blue diamonds. And then we also have a more simplistic, a poppet design solenoid. We have in black circle the exida FMEDA average, the green circles being the ARETA average and the Dow field data. And then we have a manufacturer's warranty data and a competitor certificate data. And as you can see here from the warranty data, you can see where maybe the definition of failure was not consistent, or they were assuming that they got 100% of the returns in. And you can see where that can be a little or very optimistic. Next, we're going to look at some actuators. The actuators here, as you can see, we have different types of exida FMEDAs. We have the rack and pinion, the diaphragm, the rack, the Scotch yoke, and the piston spring return as the blue triangles. We also have the FMEDA average as the black circle and the Dow field data as the green circle. And we also have two competitors' certificate data numbers on the chart, and with a question, is it possible that they just took the manufacturer's warranty data, because it seems to match up closely with the previous slide of manufacturer's warranty data. And that possibly, we're not quite sure. I did want to make a note here that you do not see the ARETA data on this chart. ARETA publishes data as a valve, actuator, solenoid, and the piping around, and that is one system, and that's how they publish their data. So we weren't able to extract just what the actuator was. We cannot say what their actuator and how ours lines up with that, but we were able to take their valve, actuator, solenoid combination and create that combination with our, try to match the same boundaries with our data. So as you can see, we have a ball valve, a solenoid, and an actuator, and we have the different exida FMEDAs, along with the generic and the mean, along with the new 2015 ARETA data, along with a competitor's data on that graph. We can also look at IR flame detectors. So we have the exida, mean, and generic, along with a bunch of different FMEDAs that we've done and ARETA's data point. And as you can see, there's kind of a large range in the FMEDA data points. And as you can imagine, we have more complex designs and more simplistic designs all grouped together in the IR flame detectors here. So when we are compared to ARETA, a lot of people ask about, well, ARETA publishes a Topside book and a Subsea book. How do you account for that? And how do you account for the differences between the different situations? And we go back to the exida profiles, or the environmental profiles. As you can see, I zoomed in on that big chart that we looked at earlier. I zoomed into the top and the different description of the exida profiles. And as you can see, we have an offshore, a subsea, process wetted, general field mounting, and cabinet mounted. And that is how we take into consideration the topside or subsea. So we can look at each valve or actuator design in profile 4 for subsea, or profile 5 for offshore, or both. Now you might be wondering, well, I've noticed on some of the charts there are some differences. Well, why are there differences, and what could make these differences? A lot has to do with maintenance capabilities from different companies. Each company has different timelines and different ways to do maintenance. Some companies might be more serious when it comes to maintenance. Some companies might not take it as seriously as others. And maintenance, some studies show that maintenance can actually, the difference in maintenance from facility to facility can actually have 50% difference. So you could almost double your failure rates if from a poorly maintained company to a very well run, maintained company. Another difference to note is the equipment boundaries of the assemblies. As I spoke, ARETA doesn't have just an actuator data. They have the valve, the actuator, the solenoid, the piping, and a few other things put together in what they consider one system, or a large, they have the dotted lines around their boundaries. So we try as best we could to put the same group together in the same boundaries, but I'm sure there always are going to be slight differences. Now we're going to talk about, why is realistic data important? Once again, we're going to look at the zoomed in safety design life cycle. And we're looking at step 11 here. It's the calculations. It's the SIF concept. It's the reliability calculations, the safety calculation. And the step below that, these calculations are direct result in if the SIL is achieved or if risk reduction factor is achieved. So once again, if you put garbage in, you're going to receive garbage out. So if your failure rate database or the failure rates that you put in for these safety calculations aren't any good, neither is going to be your risk reduction factor or your SIL level, that you think that you got this great SIL or this great risk reduction factor and you're doing a great job, but if you're using garbage numbers in your calculations are also garbage. So we're going to, just to recap the different ways of getting failure rate data. You have your manufacturer field return data studies, your industry databases, your end user failure data studies, your B10 data points, and your calibrated FMEDA. So what is good for, I don't want to say good, but what is more appropriate for calculations? All of these are great methods to use, but what can you expect to use for calculations? There you go. Manufacturer field return data studies, great for doing root cause, but for if you're going to use that for safety calculations, you're going to be wildly optimistic. And same with B10 data. Unless you have a constant dynamic operation, you cannot use the B10 data point number. If you have a great industry database that covers what you need, and user field failure data studies with a lot of information, or a calibrated FMEDA, those all will give you reliable and trustworthy failure rates. So what happens if you find yourself in a situation when the numbers that you receive or the calculations that you're doing don't seem realistic? What do you do? Well, the first thing I always suggest is always question it. Always, always, always. It is your ethical responsibility as an engineer. I don't care if you're questioning us, exida. Question me, please, if you don't think it is right. I would love to have a discussion with you about this. Any of our engineers would. If you think that your competitor or your company or your boss has given you wrong numbers, it is your responsibility as an engineer to question it. That is why you went to school. These calculations are going to be used in safety systems. This could be, if you're wildly optimistic, it could be a major disaster on your hands. It could be somebody's life. And when you take into consideration that, I don't understand how anyone couldn't question it. So if you have any doubt, question it. You can be wrong. Who cares? But what if you don't question it and you were right that it was unrealistic? The next point is just do some sanity check calculations. They can be extremely simple. Well, okay, this isn't supposed to fail, but once every so many hours. That leads to, let's see, this many years without a failure. Does that make any sense? Is that what we see in real life? If you're doing a calculation and it says it's not going to fail for 160 years for a valve, is that what we see in day-to-day life? No, that doesn't seem quite right. The next point I want to make is always compare it to actual field failure data or generic failure rate data. Go back and say, okay, this 160 years, so that means all of the valves you've ever sent out, you've never received one back because you're not even a 160-year-old corporation. Wonderful. Wait, you have returns each year? Or compare it to generic failure rate data. We're really, really excited. Part of the 4th volume of the SCRH is going to be a generic failure rate book. We have been putting countless hours and research hours into these generic failure rates. We're really, really excited about this book coming out in the 4th quarter. And finally, go back to the source of the data and try to determine what method was used to define the failure rates, and if that method is something that would work for you. Go back and see if maybe it was cycle testing hours. Well, do you have a low demand mode operation or a continuous demand? If you have a continuous demand operation, great, use those numbers. If it's a safety system or you have a low demand operation, you might want to go back and find numbers that weren't figured by the B10 or cycle testing. So, of course, I was a bad person and did not look at questions. So we're going to now look at questions, and if you have any, let me know now. And if you think of any later on, please email me. I would be glad to email you back whenever I get a moment about the questions. I had somebody ask, what is the x-axis in this graph? I think I know the answer, but I'm going to go back to the x-axis in this graph is just the number of data points that we had. I was trying to make these graphs very quickly for this webinar. So it is the 1 through 20 is the number of points that we have on the graph. The 100 through 10,000 is in bits. So I should have labeled that, I'm sorry. If there's any other questions. Oh, I have one more, hold on. What do you do when there is no failure rate data for some mechanical components, like a contactor or a motor contact? I would look at field return data and make an assumption that you're not going to get a lot of data back, and try to be as conservative as you are and do calculations that way. But I think if you look into it, you will find yourself information. I know that we do have failure rates for a contactor, and I think we have for a motor contact also. So I would research that a little bit more, and if it's something that is completely new and innovative on the market, I would look into field returns, but just please be very conservative on your assumptions that you are making, because you never know when. You would always rather be conservative than not conservative enough and somebody get hurt. Those are all the questions I have for now. If you think of any others, please email me, and thank you for joining in.